Just as we had damped springs and pendulums where there was a loss of energy and it would go towards its equilibrium and stop, we also have damped LC circuits, and that's by adding in a resistance. So notice here this resistor in series with this LC, inductor and capacitor. And if we go to write the differential equation, it would look like L dq, I should say second derivative of charge with respect to time over dt squared plus r dq over dt plus q over c equals 0. And our normal form is to take and bring L through, divide everything by L. And I'm not going to go through all the derivation. This should look very familiar from what we did in chapter 14. What we find is that we have omega prime. I use this only because Giancoli does. I prefer using omega d for omega damped. And that is going to equal the square root of our pure oscillation, which is going to be 1 over LC. And then we add the damping term, r squared over 4L squared. So our oscillations are going to be a little bit slower because of this resistance. And our formula for the charge is Q equals Q naught E to the negative, negative RT over 2L times the cosine of omega d t plus V. Now we can also extend this because of Q. I can do the derivative of this, and that would get me the current. And actually this should be Q function of t here. And don't forget that because this is a function, actually a function of two functions of t, you're going to have to use the product rule to do this. Now, just as we had with the springs and pendulums, we still have the same definitions for the different types of results. Here we have also what we call the underdamped. and that occurs when R squared is less than 4, 4L divided by C. We have the critical damped, and that happens when R squared is equal to 4L divided by C, and overdamped when R squared is greater than 4L, wrote that wrong, sorry, 4L over C. And we still have the same graph as we had, and I forgot to copy it over, but we can look at it in the presentation. So here, this looks exactly like the same graph that we had previously for the underdamped A case, the critically damped, and the overdamped. These all have the same definitions as we had for the spring. So we're back to chapter 14 and a lot of things here, but it's all makes, all comes together, making sense between the mechanical and the electrical. Everything works the same way when we're talking about oscillations.